Good morning, everyone. My topic today is all about the Mobius inversion formula. So, without so much further ado, I start to introduce to you what is the Mobius inversion formula. The Mobius inversion formula is a relation between pairs of arithmetic function, each defined from the other by sums over divisors. The Mobius inversion formula, we introduce another naturally defined function on the positive integers, the Mobius mu function. Definition 623, for a positive integer n, define mu by the rules mu of n is equal to 1 if n is equal to 1, 0 if p squared divides n for some prime p, negative 1 raised to the power of r if n is equal to p sub 1, p sub 2, p sub r, where the p sub I are distinct primes. Put somewhat differently, definition 623 states that mu of n is equal to 0 if n is not a square-free integer. Square-free integer is an integer which is divisible by no perfect square other than 1, while mu of n is equal to negative 1 raised to the power of r if n is square-free with r prime factors. For example, mu of 30 is equal to mu of 2 times 3 times 5 is equal to negative 1 raised to the power of 3 is equal to negative 1. The first few values of mu are mu of 1 is equal to 1, mu of 2 is equal to negative 1, mu of 3 is equal to negative 1, mu of 4 is equal to 0, mu of 5 is equal to negative 1, mu of 6 is equal to 1, and so on. If p is a prime number, it is clear that mu of p is equal to negative 1. Also, mu of p raised to the power of k is equal to 0 for k is greater than or equal to 2. Theorem 6 to 5, the function mu is a multiplicative function. Proof. We want to show that mu of mn is equal to mu of mu of n whenever m and n are relatively prime, which is prime is a prime number is a natural number greater than 1 that is not a product of two smaller natural numbers. If either p squared divides m or p squared divides n, p a prime, then p squared divides mn, hence mu of mn is equal to 0 is equal to mu of m, mu of n. And the formula holds trivially. We may therefore assume that both m and n are square-free integers. Say, m is equal to p sub 1, p sub 2, p sub r, n is equal to q sub 1, q sub 2, q sub s, the primes p sub I and q sub j being all distinct, then mu of mn is equal to mu of p sub 1, p sub r, q sub 1, q sub s is equal to negative 1 raised to the power of r plus s is equal to negative 1 raised to the power r, and negative 1 is equal raised to the power of s is equal to mu of m and mu of n, which completes the proof. Let us see what happens if mu of d is evaluated for all the positive divisors d for an integer n and the results added. In case n is equal to 1, the answer is easy here. Sum of d divides 1, mu of d is equal to mu of 1 is equal to 1. Suppose that n is greater than 1 and put f of n is equal to and put capital F of n is equal to sum of d divides n mu of d. To prepare the ground, we first calculate capital F of n for the power of a prime. Say n is equal to p raised to the power of k. The positive divisors of p raised to the power of k are just the k plus 1 integers 1. P squared p raised to the power of k, so that capital F of p raised to the power of k is equal to sum d divides p raised to the power of k, mu of d is equal to mu of 1 plus mu of p plus mu of p squared plus plus mu of p raised to the power of k is equal to mu of 1 plus mu of p is equal to 1 plus negative 1 is equal to 0. Since mu is known to be a multiplicative function, an appeal to Theorem 6 to 4 is legitimate. This result guarantees that capital F is multiplicative too. Thus, if the canonical factorization of n is equal to p sub 1 raised to the power of k sub 1, p sub 2 raised to the power of k sub 2, p sub r raised to the power of k sub r, then capital F of n is the product of the values assigned to capital F for the prime powers in this representation. Capital F of n is equal to capital F p sub 1 raised to the power of k sub 1, capital F of p sub 2 raised to the power of k sub 2, capital F of p sub r raised to the power of k sub r is equal to 0. Theorem 6 to 6. For each positive integer n is greater than or equal to 1, sum of d divides n, mu of d is equal to 1 if n is equal to 1, 0 if n is greater than to 1, where d runs through the positive divisors of n. For an illustration of this last theorem, consider n is equal to 10. The divisors of 10 are 1, 2, 5, 10, and the desired sum is sum of d divides 10, mu of d with mu of 1 plus mu of 2 plus mu of 5 plus mu of 10 is equal to 1 plus negative 1 plus negative 1 plus 1 equals 0. So, ang pagkuha ni sa value diri sa kaning 1 plus negative 1 plus negative 1 plus 1 is equal to 0, mo tong value nga nasa unahan sa previous nga akong giingon ninyo nga kani nga page. Kani siya. Bali dito ni bali katong value to dito nga akong gi-mention, bali dito siya gikan. So, let's proceed. The full significance of Mobius function should become apparent with the next theorem. Theorem 6 to 7, Mobius inversion formula. Let capital F and little f be two number theoretic function related by the formula. Capital F of n is equal to sum of d divides n f of d, then little f of n is equal to sum of d divides n mu of d, capital F of n divides d is equal to sum d divides n mu of n divides d, capital F of d. Proof. The two sums mentioned in the conclusion of the theorem are seen to be the same upon replacing the dummy index d by d prime is equal to n divides d. As d ranges over all positive divisors of n, so does d prime. Carrying out the required computation, we get, this is the equation 1, sum of d divides n mu of d, capital F of n divides d is equal to sum d divides n of mu of d, sum of c divides n over d, f of c is equal to sum over d divides n of sum c divides n over d mu of d, little f of c. It is easily verified that d divides n and c divides n over d if and only if c divides n and d divides n over c. Because of this, the last expression in equation 1 becomes in equation 2. Sum of d divides n of sum of c divides n over d mu of d, little f of c is equal to sum c divides n of sum d divides n over c of little f of c mu of d is equal to sum c divides n of letter f of c sum d divides n over c mu of d. In compliance with theorem 6 to 6, the sum of sum d divides n over c mu of d must vanish except when n over c is equal to 1, that is when n is equal to c, in which case it is equal to 1. The upshot is that the right hand side of equation 2 simplifies to sum of c divides n of letter f of c sum of d divides n over c mu of d is equal to sum c is equal to n of letter f of c times 1 is equal to letter f of n, given as the stated result. Let us use n is equal to 10 again to illustrate how the double sum in equation 2 is turned around. In this instance, we find that sum of d divides 10 of sum of c divides 10 over d mu of d f little f of c is equal to mu of 1 little f of 1 plus f of 2 plus f of 5 plus f of 10 plus mu of 2 f of 1 plus f of 5 plus f of 5 f of 1 plus f of 2 plus mu of 10 f of 1 is equal to f of 1 mu of 1 plus mu of 2 plus mu of 5 plus mu of 10 plus f of 2 mu of 1 plus mu of 5 plus f of 5 mu of 1 plus mu of 2 plus f of 10 mu of 1 is equal to sum c divides 10 of sums d divides 10 over c of little f of c mu of d. To see how Mobius inversion works in a particular case, we remind the reader that the function tau and sigma may both be described as some function. Tau of n is equal to sigma d divides n 1 and sigma of n is equal to sum of d divides n d. Theorem 6 to 7 tells us that these formulas may be inverted to give 1 is equal to sum of d divides n mu of n divides d tau of d, and n is equal to sum d divides n mu of n divides d sigma of d, valid for all n is greater than or equal to 1. Theorem 6 to 4 ensures that if little f is a multiplicative function, then so if capital F of n is equal to sigma is equal to sum d divides n little f of d. Turning the situation around, one might ask whether the multiplicative nature of capital F forces that of little f. Surprisingly enough, this is exactly what happens. Theorem 6 to 8. If f is a multiplicative function and f of n is equal to sum of d divides n f of d, then little f is also multiplicative. Proof. Let m and n be relatively prime positive integers. We recall that any divisor d of mn can be uniquely written as d is equal to d sub 1 d sub 2, where d sub 1 divides m, d sub 2 divides n, and GCD of d sub 1 d sub 2 is equal to 1. Thus, using the inversion formula, little f of mn is equal to sum of d divides mn mu of d capital F of mn divides d is equal to sum of d sub 1 divides m, d sub 2 divides n, mu of d sub 1 d sub 2 capital F of mn divides d sub 1 d sub 2 is equal to sum of d sub 1 divides m, d sub 2 divides n, mu of d sub 1, mu of d sub 2 capital F of m divides d sub 1 capital f of n divides d sub 2 is equal to sigma d sub 1 divides m. Mu of d sub 1 capital F of m divides d sub 1 sum of d sub 2 divides n. Mu of d sub 2 capital F of n divides d sub 2 is equal to f of m and little f of n, which is the assertion of the theorem. Needless to say, the multiplicative character of mu and of capital F is crucial to the above calculation. So, my topic is all about the two formula, which is the little f and capital F, the inverted in each other. So, which means invert is the reverse in position, order, or relationship. That's all. Thank you for listening.